It's time for another episode of Math on the Sphere. Episode 9, Area Basics Review. So far, the focus of this series has been all about solving the spherical triangle. Solving the triangle has certainly gotten this far, informing us how the arcs and angles between points on a sphere relate to one another, and helping us to navigate among them in a variety of situations. But now it's time to shift our attention to another quantity of interest, the area, which on the sphere delivers a new beauty and elegance of its own. The concept of area is most likely not new to you, but I've held off on introducing it until now. Area measures the size of arbitrary two-dimensional regions in terms of how much surface they cover. In English, the words area and arable have a common Latin root related to vacant pieces of level land and the act of plowing fields. If you consider the ancient origins of geometry, the handling and management of crop-producing land areas was without doubt the most critical practical application, the necessity behind its invention. Now consider a plane and its most basic closed shapes: squares, rectangles, triangles, and circles. A shape's area measures the amount of planar surface contained within it. The basic unit of area is the square, and in practical terms, lengths and areas are entirely different beasts. To see this, suppose I have a square that is 1 inch long on each side, and I ask you how many inches of area it covers. Well, the inch is a measure of length, so let's attempt to fill our square using an infinite line. I'll chop the line up into 1 inch pieces and line them up side by side until I fill the square, counting as I go. Will this work? Remember, the width of a line segment is 0, so after I've added 1,000,000 or even 1,000,000,000 of them side by side right up against each other, the total width is still 0. The only way to measure the size of a square is to conceptualize a new unit, a square unit, having the original unit as its length and width. I define this area here as 1 square inch, and then I can measure any other region as some non-negative multiple of it. For squares and rectangles of arbitrary size, the area is found by multiplying the length by the width, with these two quantities being identical in the case of the square. For triangles, one of the three sides is designated the base, and the height is defined as the distance between the line containing the base and the other triangle point, the one not on the baseline. The height is measured along a perpendicular line, and that measured perpendicular segment is called an altitude of the triangle. The triangle's area is 1/2 the length of the base times the corresponding height. To see why this area formula works, it's easy to construct adjacent congruent triangles that total the same area as our original, and each share an edge with it, in such a way that the entire combination is a rectangle having a base and the height as its dimensions. Then, since the adjacent areas add, twice our triangle's area is the area of the rectangle. For the circle, we can find the area using what we already know about the circumference, using a method that was introduced by Archimedes over 2,200 years ago. Imagine chopping our circle with radius r up into a large even number of pi piece-shaped wedges, and then putting all the pieces side by side in an alternating pattern that looks like a rectangle, so that the circle's circumference is divided equally into the top and bottom edges. As the number of pieces increases and the size of each piece decreases, this shape becomes closer and closer to a true rectangle, having a length of pi times the radius and a height equal to the radius. The area of this triangle is just pi r squared, and it's equal to the area of the circle. For our last trick, we'll come up with the formula for the surface area of a sphere. This was also first discovered by Archimedes, and it's quite an amazing result. To do this, we first need to introduce a new three-dimensional shape, the cylinder. You probably already know that the most common cylinder looks like a soup can, with two circular caps and a curved lateral surface connecting them. But this is actually a special case. More generally, a cylinder has two caps in parallel planes, which are always congruent and most often circles, though they may also be elliptical. The lateral surface is an extrusion of the cap's shape Between the two planes, taken along the axis, the line segment connecting the two caps is centers. When the axis is perpendicular to the caps, you have a right cylinder. Otherwise, you have an oblique cylinder. The cylinder's height is the distance between the planes containing the caps, and the base is the shape of each cap. For our purposes, we're going to need a right cylinder having a base that is congruent to our sphere's great circle, and a height that equals the sphere's diameter.